This is Wonder Boy running on an SG-1000, and this is Wonder Boy running on a Sega Master System. Both of these systems are 8-bit and in fact even share the same 8-bit CPU, so why do they look so different? In my previous video, we explored why the same SG-1000 game running on original hardware looks fine, but looks off when played on the backwards compatible Master System. But what allows a game designed for the Master System to have so much more detail than an SG-1000 game if they're both 8-bit systems? The term 8-bit is mostly an aesthetic word these days, but when talking about consoles from the 1980s, 8-bit actually refers to the CPU that runs the console, the heart of the system, if you will. The CPU is responsible for moving data and performing calculations. It rarely, if ever, has anything to do with graphics output unless software tricks are being done to create special graphical effects. The Visual Display Processor, or VDP, is the main driving force behind what gives any console its identity, at least when talking about graphics. The SG-1000 and Sega Master System are a perfect case study for this. Both systems have the exact same CPU, the Zilog Z80, but have remarkably different VDPs. Let's follow the path of history and start with finding out what kind of restrictions the SG-1000 is working with. The VDP of the SG-1000 has a palette of 16 predetermined colors and, like many 8-bit systems of the era, uses tile-based graphics for most of its games. Although we have 16 colors to choose from, there is a bit of a strict limitation with how we're able to use them. The graphics tiles of the SG-1000 actually only have 1-bit color depth, meaning a pixel can either be turned on or turned off. But wait, if that's the case, then how can we make such colorful graphics? Well, for every tile in the VDP's memory, there exists a corresponding color byte. Since our color palette is made up of 16 colors, we can just perfectly represent 2 of these colors using a single byte, with 4 bits being used to define the index of a single color in our palette. This means that the on or off pixels of our tile don't have to just be black or white, but rather can be green and blue, red and cyan, or any combination of 2 colors that we want from our palette. But the VDP actually lets us take it a step further, because instead of just 1 color byte per tile, we actually get 8, meaning that all 8 rows of a tile can have their own 2 unique colors if we so choose. This is the reason why so many SG-1000 games have that classic layered color text, like in Gull Cave or Wonder Boy. All you have to do is keep the background a consistent color, and you can then make a gradient over your text using the color bytes. Similar to how tiles get mapped with color using color bytes, the main display gets mapped using tile map bytes that point to tiles in VRAM using their tile index. Generally speaking, a byte can hold any value between 0 and 255, but with up to 768 tiles mapped to the screen, the SG-1000 can't possibly support a full screen's worth of tiles using just a single index byte. So instead, the map and the tile data are divided into thirds respectively. The top third of the display will only ever be able to use tiles that are mapped to the top third of VRAM, and the same goes for the second and final thirds of the screen with their corresponding VRAM sections. This means that if you want to use the same tile across all 3 sections of the screen, then you have to write the pattern to VRAM once for each section you want the tile to be displayed in. This may seem wasteful, but this design means that the SG-1000 is capable of displaying 768 unique tiles at once, an entire screen's worth, and allows for basic bitmap drawings. With all of this in mind, as long as we adhere to the limitations, it's actually quite simple to create a program that can turn images into data that the SG-1000 can read. When it comes to designing pixel art graphics, my weapon of choice is Sprite, as it is specifically designed for pixel art and allows for user-created scripts to be made, making an already feature-rich application only limited by your own programming skills. Or your ability to convince someone else to make programs for you. By reading through the official TMS 9928 manual, I was able to get a script running that can export ink files for tile patterns, tile maps, and color maps, and it's what I've been using in development for my SG1000 project. A download link is in the description, by the way. As for the Master System, it mostly supports the SG1000's graphics mode for the sake of backwards compatibility, but there exists at least one SMS game that uses this mode for its main graphics display, that being F-16 Fighting Falcon. Aside from that title though, most Master System games use a different graphics mode called Mode 4. In Mode 4, the SMS contains two 16-color palettes, both of which can pick any combination of 16 colors from a total list of 64 colors, with one palette intended for background tiles and one intended for sprite tiles. While the SG1000 simply used a single bit for an on or off state to determine pixel color, the SMS instead uses 4 bits per pixel to determine its color. These 4 bits can, in total, hold any value between 0 and 15, and thus point to a specific index in our 16-color palette to determine what color any given pixel should be. The Master System also makes use of a tile map, but this time uses 2 bytes per tile map position instead of just 1. The Master System uses only 9 bits, numbered 0 to 8, for determining which of a possible 448 unique tiles to draw to the 768 tile display, but why does it do this? Well, bits 9 and 10 are used to set a horizontal or vertical flip. Instead of storing the horizontal, vertical, or diagonal mirror image of a tile in VRAM, the Master System allows programmers to save VRAM space and flip the orientation of the tile when drawing to the tile map just by setting 1 or 2 bits. Though they aren't unique tiles per se, this triples the amount of patterns we can make and can really save a lot of space if you design your graphics with this in mind. In addition, bit 11 allows the programmer to select the background palette or sprite palette for any given tiles, again allowing for potentially much more colorful graphics. But my favorite graphics trick of the SMS's tile map belongs to bit 12, the background priority bit. When this bit is set to 0, it acts as you would expect any game to, where sprites are drawn over the background. But when this bit gets set to 1, sprites will only be displayed on top of the 0 index background color. A really cool example of this is in the tattered doors on level 3 of Ninja Gaiden. As Ryu passes into the building, we can see him running behind the tears in the sliding doors. What's actually happening is these tiles have their background priority bit set to 1, so Ryu's sprite only appears on the black 0 index background color. This is the exact trick I used to get the shimmer to appear only over the metallic portions of the Steelfinger Studios logo. The final 3 bits, numbered 13 to 15, serve no purpose, but can be used by the programmer if they so desire. With this in mind, you could do something like make certain tiles have no collision for hiding secrets, or make them breakable, or set any kind of interaction you could think of. The limit is simply with your own creativity. While this is a fairly accurate explanation of how SMS graphics work, I have simplified some aspects and left out some confusing technical details and complexities in order to make things easier to understand. If you're interested in a deeper dive into the complexities of Master System graphics storage, let me know. I'd love to dive even deeper into the bits and bytes if there are people who want to know about it. I spent a lot of time researching how the SMS handles its graphics for this video, and especially for getting a script to export graphics from Sprite. This proved to be a bit more of a challenge with the SMS than it was for the SG1000, mostly from some slightly confusing wording from the official documentation and my hasty reading of the portion on how tile data is stored. However, in the end, I was able to get one working. Now, with a way to export graphics for both systems, I was able to move on to the next step in my SG1000 and SMS compatible game project. My goal for this project is not to have visually distinct graphics for each system, but rather to have a single SG1000 game that looks and feels like an SG1000 game when played on either system without the dark, oversaturated colors that the Master System's Legacy mode induces. So, with my new Sprite script for Master System, I was able to design a palette that matches much more closely to the SG-1000 original and create a Steelfinger Studio splash screen that, although not identical depending on what hardware you're playing it on, looks as close as it can possibly be to an SG-1000 game when running on a Sega Master System. Now that I'm armed with a way to quickly get graphics up and running on both of these systems, it's time to start working on the actual gameplay. If you're interested in following this project as well as all of my other 8-bit assembly adventures, consider supporting me on Patreon for access to my weekly development videos. I'm Bofner, and thanks for watching. See ya!